Hey there, math fans. This is Dr. Andy Lovelace. This is more of a general video based off of a question a student was asking me. Why do we even use an error bound for Taylor polynomials? Why don't we use the exact value? I can even give you the formula for the exact value. Why don't we use it? And where do error bound come from? And why is it an integral? These are the sorts of questions people are asking me. So I thought I would just take a little different approach here and explore. And this is based off of a question a student asked me. So there are two examples there. The Taylor polynomial for e to the x, the pattern we get, and I've given you the exact error, meaning this is not a bound. This is precisely what it is here. If you can compute that integral and you plug in an x here and plug in the same x here and here, this integral will give you precisely the error. Now you might say, where does that come from? I'll show you that in a moment, but that's more theoretical. I thought rather than jump into that, it would be better to start with an example. Now that one's not that interesting. To me, more interesting is like a place where we'd use it. Like this is a function that's a very important function that's sometimes hard to work with, and so we often give a Taylor series. So we get this, but the bad part is you would need the 11th derivative here. And I took that, and I'll talk about that in a second, but the 11th derivative is not nice. Okay, so I'm going to talk about this a little bit and play around and finish with some theory. And then I'll probably have a short follow-up video I will make for that particular student. So Micah, thank you for asking this question. So just some visuals. We found this pattern. It's very fun to look at. We tend to just draw the polynomials, and you can see them approaching very quickly, that function. And then we say there's an error between them, the vertical gap. They're not the same, but the error is getting smaller as we go. Okay, so there we're back to this. You can actually give that error. So I could give you that, I can compute that exactly as that integral. So I set all these up in here. So here's the tangent line. I'm going to base it at 0 for now. So there's our tangent line. Here's the tangent line plus the error. So if I add in that integral, it's the exact same original function. That integral added at each spot is that. Now if you just graph the error, that integral, compute a bunch of values for it, it looks like this. So that's kind of weird. The error is actually 0 in the middle, that red dotted thing. So if you add that to the purple line, you get the original graph. That is it exactly. Okay, so what do we do? That's not, that sort of user-friendly. So what we do is we find the biggest this can be. And that's the part that confuses students in using this, because the moment you do that, you lose precision. So we basically say, I'd like to pull this out and simplify things. So we replace this one piece with something simpler. So in this case, we would replace this. If let's say the interval is -1 to 1. I'm getting too into the bound. That wasn't my goal. But let's say the interval is x is between here and here. Then we would say the biggest this can be is e to the 1. Now the moment we do that, we lose the plus and we get this inequality. We say it can be up to this. So then we write approximately. Or what we really do is we say the difference between these two things is equal to this. But if we want to replace that, then it becomes less than or equal to. And that gives us something nicer. So in this case, we would just say, well, what if we just call this e? And then we integrate. And when you integrate, this becomes an 11, and there becomes an 11 here. So the bound becomes e over 11 factorial. So there's really like breaking down what happens there. All right. So this one's much worse, though, because the 11th derivative is going to be messy. But so that's a little bit about the error bound and kind of some examples. It's fun to see the precise formula. and I'll just show you this other function and why it's interesting. And then I'll show you a bit about where it comes from. And I'm going to see where that takes me. So there's the e to the negative x squared. It's this bell-shaped curve. That's why it's important. That's where the bell curve comes from. We can find the Taylor series for this. We can really do it for just about anything here. And it goes out and hugs it. You can see the error actually gets really... Surprisingly, this one has a much worse error than the other one as you go further out, because the graph really flattens out as you go out. It's curviest in the middle. Polynomials don't do that very well. So there's a pretty big error when you go far out, but it's not much of an error when you're close. Okay. That's the game. But the same ideas apply. So I can graph the first Taylor polynomial. That's that line. I can graph the Taylor polynomial with the error added in, the error integral, and it gives exactly the same function. Or we can do a bound on that. All right. So in this case, I just did it numerically. I found, I'm going to get rid of this picture for a second. I found the 11th derivative. I had just asked Wolfram Alpha to find it. I asked for the maximum of the 11th derivative, and it got 1, 3. So this would be like a very particular example. For some reason, I want to use the 10th derivative here. The 11th derivative is maximized at 0.314, so it's not at an endpoint or anything. So this would not be something I would do or ask students, but I just wanted to give another example. So for this one, you would say that, well, the biggest this can be on the interval -1 to 1 is 131,846. And then when you integrate, you'd get an 11 factorial, you'd plug in the value. So you end up getting that over 11 factorial is your bound, which is this. Oops, that's e over 11 factorial. 11 factorial is really big. It's this number. It's bigger than that number. So anyways, if you're using this on the interval -1 to 1, you can be confident that it's always going to be accurate to 2 digits, 0.003. So that's the whole idea, is to try to turn that messy formula into a number, something we can quantify. So basically we can say, all right, that's too messy to work with, but if I'm only working with numbers between -1 and 1, then I can just replace this with plus or minus 0.003. So it's a measure of like trying to get a one number snapshot is what that's happening. So there is a precise formula. It's just the precise formula is not user friendly. Okay, so let's finish this with a little bit of where that comes from. And I don't think I have a complete answer for the student that's asking me this, but it comes from here. This is the fundamental theorem of calculus that says if you want to do an antiderivative, you integrate and you evaluate at the endpoints. We do something clever. We do integration by parts to turn this into a second derivative, which is not something you normally do with integration by parts, where you make things worse. When I set up integration by parts with students, we are typically trying to make things look better, not worse. But it serves a very particular goal here. So we're going to say this is the first derivative, so its derivative is the second derivative. And then we're going to say this is dt. Now the part I always find hardest to remember about the proof is that the x we're treating as a constant when we're doing this. And it makes things easier if when you integrate you do t, I think it's minus x. So there's an adjustment, or x minus, anyways, that there's, yes, it's t minus x. So you choose a constant other than 0, which we don't normally do. But the point I wanted to make is not to go into that, which is, I just wanted to say it's integration by parts. We put these two things together, and the clever observation here is that this is, if we move this to the other side, that's the first Taylor polynomial. And there is the precise integral. And so you put all that together, and that's where this all comes from, is we have a precise integral, but the 11th derivative tends to be messy, so we're going to replace it with a number. And nothing stops you there. You can do integration by parts again and again and again. I think there is sort of an interpretation of this integral. It's like a weighted integral, kind of like a moment or what, I don't know what we call this. But it's weighting this second derivative by this linear function. And if you keep going, if you go to the next term, it looks like this. So if you do integration by parts again, you get the third derivative, you get a half and a 2 from doing that integration by parts again. So it's you're weighting the third derivative by this square. So it has to do with what you're truncating. And you can just keep going. So the proof just says this can be continued. And if we find a maximum of this over the interval, we can pull that out, we can integrate again, and we get Taylor's inequality. So that's where it comes from. But I think I don't say enough that there's a precise formula for the error, but it involves an integral, and so it's not very practical for us to just give an idea of how good is this. All right, I hope there's some interest there. Let me know. I feel like I'll need to do this again in the future, but let me know if any of that helped you understand that better.